Well, hello, Engineering 203. I wanted to talk about laboratory number 2. This should play out very similar to if we were actually meeting for lab and whatnot. So that shouldn't be a lot of difference there in that you're going to just do the simulation on the computer, and that's what we've done for years, even when we were meeting. Let's look at this. You've got 4 problems that represent different types of material. The first problem here is a DC problem, and you're asked to find the current I0, which should be pretty straightforward. The second problem is an AC problem. Typical AC problem spices it up a little bit here with a voltage-controlled current source, and you're looking for this voltage out here, V0. Anytime that you explore some new software and do something like that, you probably want to have a baseline. So I highly recommend, I think it's imperative that you work these problems by hand so you know whether you're getting the right answer or not. Many times when I've been thinking about turning something over to a computer, I take a test problem, I work it by hand, I use the computer then and see if I get the same answer. I think that's important. Not that the computer would be wrong, although sometimes computer programs are wrong. It's just a test and make sure that the same inputs and assumptions and whatnot that you use are the same ones that the computer uses. If we look at the second 2 problems, you've got a 3-phase problem where you're looking for the phase voltage here across the load and the line current through the load. And finally, the last question is a mutual problem. Mutual inductance between these 2 inductors, and you're looking for that current there, I0. I tried to help you with these. If you go to the website, Engineering 203, under the Lab subtab, there's a file, LT-Spice Circuits, and you'll actually find these. And these hopefully will be a huge amount of help and avoid a lot of frustration with these problems. So a couple things as we go through these. This is a dot command, so if you have a dot and some commands, that's the way you can get it to do something. There's other ways of doing it. This is a little bit old-fashioned, but that's what that is. One thing that every circuit needs is it has to have a reference to 0. So this is going to be a 0 node down here, and you have to have that ground, that reference. Moving on to the second problem, you will see that we have the voltage-controlled current source, so we put where the sensing voltage is for that, and then we've got that with the G, that's the designation, and you can look that up in the elements and whatnot. And again, this is how we get it to run at 60 cycles. The last 2 examples are a little more involved. The 3-phase problem, if you looked at this, you might say, well, what's this super small resistor doing? This is 1 times 10 to the minus. Why is that in there? Well, if you have no resistors in here like the original problem statement was, you end up with a loop of voltage sources, and the software is not going to like that. It can't deal with that. So we fool it by putting these resistors in here, and 1 times 10 to the minus 12 is not going to change the results of the problem at all. One thing, LT-Spice, and I would really recommend most of you use LT-Spice. If you choose to use P-Spice, all I can give you is sympathy. It's been years and years since I've used that one, so I'd recommend using the LT-Spice. The LT-Spice does recognize the prefixes, although I tend not to use them because I've had some problems with them in the past. So just a bit of a warning there. So that's why I don't use the pico or the micro. Speaking of other things, make sure that you got the reference ground there. And then also these inductors, you can flip them as you're building them. You'll notice that you can flip them, and this inductor is not equivalent to that inductor. So be careful if you're struggling and you're not getting the answers that you think you should be getting. Really look at the direction of those, and that becomes very important when we go to this last problem with the mutual inductance, because it's going to dictate how the dots line up. And speaking of that mutual inductance, I'll make sure that this is on frame here. The term here, and the way this mutual is done, is it's the K term, and that K comes from the coefficient of coupling. So you have K, and then the 2 inductors that the coefficient of coupling is between, inductor 1 and inductor 2, in this case L1 and L2, and what that coefficient of coupling is. Well, how in the world do you get that? Well, you can work it backwards. You're given in the problem the individual, the self-inductance L1 and L2, and the mutual inductance. And remember, we saw the equation in this direction, that the mutual mutual inductance was equal to the coefficient of coupling times the square root of L1 times L2. So if you rearrange that equation, you can get that coefficient of coupling there, and that is that term that you will see right there. I think that's it for tricks and tips on these. One thing that you may want to think about is dividing and conquering on this, maybe having a few students tackle problem 1 and a few tackle problem 2, and so on, and not just then copy, don't just send each other the files, but show each other the tricks and tips to getting through those, because once someone's figured out the problem, they can really lead the way very quickly with that. Quite frankly, probably the biggest struggle in the past was doing the problems by hand. It seems like it's been a few weeks or months since we've done problems like that by hand, so you really need to do that so that you know whether you're getting the right answers or not, and that's often where the struggle was. I think that's it. I'll send out the other information, and you can go ahead and get started on this. Thank you. Take care.